How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for kinetic molecular theory and diffusion/diffusion. Let's look at number one. The average kinetic energy of the particles of a gas is directly proportional to what? Well, I know that, where's my pen? Kinetic energy is equal to the 1/2 times the mass times the velocity squared. So if we're talking about average kinetic energy, this velocity is the root mean square speed. So it's not the average velocity. Something that has average kinetic energy, you go, all right, well, what is its velocity? That is defined as the root mean square speed. It is the speed at which a particle with average kinetic energy is moving. So the kinetic energy is proportional to the RMS squared. So if we take a look, it's choice E, the square of the RMS speed, the root mean square speed. So, yeah. Number two, according to kinetic molecular theory, pressure rises as the temperature of a gas increases because, well, let's see, the gas molecules collide more energetically with the wall. That is true. Things with greater kinetic energy or higher temperature will collide more energetically with the wall. B, the gas molecules collide more frequently with the wall. That's also true. If those particles are moving around more, they're going to collide more as well, right? So you increase the kinetic energy, you increase the temperature, it's moving more, it will collide more. So C is looking pretty good because it's saying both A and B, right? D, the gas molecules collide less frequently with the wall. That's not true at all. Then the average kinetic energy of the gas molecules increases. Well, that's true, but that doesn't really explain why the pressure goes up. So best answer would be choice C. Number three, according to kinetic molecular theory, if the temperature of a gas is raised from 100 Celsius to 200 Celsius, the average kinetic energy will increase by a factor of blank. So you got to remember that if we're talking about kinetic energy, it needs to be in the absolute scale, which means we need to be talking about it in Kelvin. For example, if I went from 0 degrees Celsius up to 100 degrees Celsius, what is that, 100 times more? Or well, what is 0 to 100? There's no multiple of that. But when we're talking about kinetic energy on the Kelvin scale, that's the absolute scale. So it's saying, hey, what is the ratio of kinetic energy of the second temperature divided by the first temperature? So we actually got to convert it to Kelvin. We go 200 Celsius is our second condition. So it's really 473 Kelvin divided by 373 Kelvin. We got to convert these Celsiuses to Kelvin, and then we go, what is the ratio for that? And it's 1.27 times, right? So if you go from 100 Celsius to 200 Celsius, or 373 Kelvin to 473 Kelvin, your kinetic energy has gone up by 1.27 times. Number four, which of the following gases will have the greatest rate of effusion at a given temperature? So really what it's asking is which one of these is the lightest? Which one of these is the least massive? So you got to go, hey, what are my molecular weights for all this? For CH4, it's roughly 16. For argon, it's roughly 40. For HBr, it's roughly 81. For HCl, it's roughly like 36.5. NH3, it's roughly 17. So which one of these is going to have the greatest rate of diffusion? It's going to be the lightest one. It's going to be CH4. All right, 5. What is the root mean square speed of H2S at 26 degrees Celsius in meters per second? So the equation that you're going to need is like, hey, the speed for the root mean square speed is the square root of 3 times R times T all over the molar mass. Now, the thing about the molar mass is it's going to have to be converted into kilograms per mole. Normally, we're real used to seeing it in grams per mole, but it's got to be kilograms per mole. So plug and chug. 3 square root of 3 times the 8.314 joules per mole Kelvin. Because we're dealing with like energy and speed, we're going to want to use this R times the temperature. Well, 26 Celsius is the same as 299 Kelvin divided by the molar mass, but in kilograms. So we know that it's 34.09 grams per mole, but we need it in kilograms, so we divide that by 1,000 to get it into kilograms. And when we plug and chug that, we get 468, and our units are going to be meters per second. The joules, when you square root it, you end up with meters per second. Cool. Number 6, at a given temperature, which pair of gases would have the closest rates of effusion? So what's the difference between them? The mass. So if we're talking about closest rates of effusion, we want masses to be almost equal, the most equal to each other they are. So I got to take a look. N2 and O2 is roughly, I think, like 28 versus 32. CO and CO2 is roughly, 28 versus 44. CO versus N2, I think, is roughly 28 to 28. N2 is about 28, so these are pretty close. NO2 and N2O4, well, hey, I know just this is going to be 2 times as much, so definitely not. And N2O versus NO2, let's see, 28, it's like 44 versus 46, I think. So the best answer is going to be choice C. Those masses are the closest out of all the options. And then, number 7, a tank containing a mixture of HF and HBr gases developed a leak. Oh no. What is the ratio of the rate of effusion of HF to the rate of effusion of HBr? So the Graham's law kind of thing is going to be what we want. The rate of 1 divided by the rate of 2 is going to equal the square root of the mass, the molar mass of the second one divided by the molar mass of the first one. So you just got to kind of pick which one you want to be what. So I'm going to say 1. Let's make that HF, which means 2 is going to be my HBr. So if I do the rate of 1 divided by the rate of 2 equals the molar mass of 2 divided by 1, then that's really saying the rate of HF divided by the rate of HBr is going to be proportionate to the molar mass of HBr divided by the molar mass of HF square rooted. So I plug and chug. Square root of, well, let's see, HBr is roughly 80.91 grams per mole divided by HF is roughly 20.01 grams per mole. And when I plug and chug and get an answer there, I get roughly 2.01 times the rate. So HF is going to effuse roughly 2 times quicker than HBr. Rate number 8, similar but different. A sample of 2.0 millimole sample of, we probably get rid of one of those samples, right? Of N2 gas effused through a pinhole in 5.5 seconds. How long will it take for the same amount of CH4 to fuse under the same condition? So going back to this equation again, rate 1 divided by rate 2 equals the square root of molar mass of 2 divided by the molar mass of 1. But the rate of 1 is going to equal the change over time for the 1, right? And rate of 2 is going to equal the same thing, the change divided by the time for 2. Now they're saying for the same amount, so the change is equal to both of them. So when I do, hey, the change of 1 divided by T1 divided by the change of 2 divided by T2, the changes would cancel out, keep change flip, we end up with the time for 2 divided by the time of 1 has to equal the square root of the molar mass of 2 divided by the molar mass of 1. And if we're trying to figure out how long it is, we want to solve for one of those things. So let's say T2, if I want it by itself, it's going to equal T1 times the square root of M2 over M1. So now I'm going to pick up my handy dandy calculator and start plugging and chugging. I'm going to say 1 is my N2 and my CH4 is my 2. So that I can go, hey, the time it takes for CH4 is equal to the time it takes for N2 times the square root of N2 molar mass divided by CH4. Oh wait, I did that wrong. Sorry. All right, if CH4 is 2, so it's the molar mass of CH4 divided by the molar mass of N2. So plug and chug. The time for N2 was 5.5 seconds times by the square root of the molar mass of CH4, which is what, 16.05 grams per mole divided by N2 is 28.02 grams per mole. And when I do that, I end up with 4.2 seconds. So CH4, since it's the lighter one, takes less time. Hope you found that helpful. See you in class. Okay, bye.